Good afternoon, everyone. Welcome to the Construct Innovate webinar series in sustainability planning and construction. My name is Jamie Coggins, and I'm Director of Construct Innovate, which is Ireland's National Research Centre for Construction, Technology and Innovation. And we're co-hosting this webinar with Engineers Ireland. So today's topic is around low energy buildings, and in particular, why monitor the performance of buildings is important, and the lessons learned from monitoring those buildings. We're absolutely delighted to have three fantastic speakers today. Our first speaker is going to be Dr. Marie Coggins, who's from the University of Galway, and she's going to talk about energy retrofits and factors affecting a just transition to good air quality. Then we have Simon Jones from Air Quality Matters, and he's going to talk about changing the framing of changing the framing of what good looks like through monitoring. And then Stephan from COADY Architects, who's going to touch on the RIAI Sustainability Challenge, and in particular the part of monitoring of buildings to determine the actual performance of buildings. So we're going to have our three speakers, and then after the end of the three speakers, we're going to have an open Q&A session with the speakers in there. So if you have any questions during the presentations, then please put them into the Q&A function at the bottom of the screen there. And without further ado, I'm actually going to hand over to Dr. Marie Coggins, who's going to start the first presentation. So over to you, Marie.
Okay, thank you everybody for joining us this morning. So over the next number of slides, I'm going to talk to you about the SAI funded Haven project, and the objective of Haven was to look at the health impact and associated benefits of energy renovation to B or B2. There was a number of elements to Haven. Today I'm just going to talk to you about the element that looked at pre and post indoor air quality in primarily a sample of social housing in Ireland. So the objective of Haven, of this element of Haven, was to recruit 20 social housing units in Ireland, and then to do the surveys pre and post retrofit. But unfortunately, the Haven started at the same time as the global pandemic, and so that significantly impacted on our recruitment. And also impacted on the rollout of the retrofit programs across the local authorities and the approved housing bodies. So I suppose a pre-retrofit, we had 19 social housing units, and we supplemented that number with 3 private retrofits. But then at post-retrofit, the number reduced to 14. We still had the 3 private retrofits, and we had 11 social housing units. The inclusion criteria was that non-smoking residents would be participating in the study, and the study post-retrofit surveys were done between 9 and 20 months post-retrofit. You can see there on the right-hand side of the slide that the retrofit itself had a significant impact on the energy performance of the energy performance of the home, the dwelling. So in terms of the measures that were done as part of the retrofit, it varied from home to home because some of the retrofits some of the homes had shallow retrofits in the last 10 years. And then some homes did get extra wall or roof insulation, some got some windows, some got some doors. But I suppose the common thing that everyone got was they got a heat pump, replacing their fossil fuel-based heating source. In the private dwellings, they got mechanical ventilation. So the 3 private dwellings got DCV ventilation. And importantly, just to note that they were air tightness tested before and after the retrofit. In comparison, just 1 local authority installed mechanical ventilation in 2 of the social housing units that were participating in the survey. Now they weren't air tightness tested before and after the retrofit. For, I suppose, more detail on the upgrades that were made across all the homes, we've published this work in the Journal of Indoor Environments. I'll give you the reference later in the presentation, and you can look up exactly what was completed across all the different homes. So before I talk about, I suppose, the parameters that we measured in the homes, I thought it might be useful just to familiarise ourselves with, what is indoor air. So at the latest count, there's been upwards of over 2,000 chemicals and other species of biological origin typically identified in indoor air. And this number continues to increase as we bring new products to market, and then we bring these products into furnishings and fittings in our homes. But over the last number of years, I suppose, I should say that I suppose for the majority of those chemicals, we know very little about the human health impact or the dose, what we call the exposure response relationship in humans. But over the last number of years, for a small handful of chemicals, we're beginning to understand a little bit more what exactly the health effects are. And there's been at least 3 large health impact assessments done on indoor air. And the results from the 3, I suppose, correlate well with each other. They're saying that, you know, most of the health burden due to exposure to indoor air pollutants is coming from exposure to one of these 5 pollutants. So fine particulate matter, or PM2.5, seems to be the pollutant that drives most of the health impacts, but also things like formaldehyde, radon, ozone and NO2, they're also responsible for quite a significant chunk of the health impacts that we see arising from exposure. And of course, in terms of where all this stuff is coming from, there are 3 main sources of indoor air pollutants. So outdoor air is a significant source, and particularly in Ireland for PM2.5, as we still have the burning of fossil fuels for residential heating. In the wintertime especially, outdoor air pollution is a significant source of PM2.5. But then occupant behaviour is also a significant source. So if you're smoking or vaping indoors, obviously that's going to drive the PM2.5 concentrations up also. And then building fabric. So I suppose we're thinking here in terms of the VOCs. So building fabric is a significant source of VOCs, such as formaldehyde. And that's something we're particularly interested in looking at in retrofit. So against that backdrop then, in the Haven project, this is what we looked at. So we aimed to collect 72 hours of measurement data in the homes pre and post for particulate matter, PM2.5, and also carbon dioxide, carbon monoxide, temperature and relative humidity. And all pollutants, I should mention, were measured in the main living area and the main bedroom in the home. We also collected formaldehyde data over a 3-day period in, again, the main living area and the main bedroom of the home. And the objective was to collect radon pre and post retrofit as well. But as those who have monitored radon know, it's a 3-month monitoring minimum period, sampling period. And so it was difficult to get a lot of the pre-data. So, you know, most of what we have is post data for radon. Along with collecting the measurements, the researchers spent between 2 and 3 hours in the home with the homeowner or the head of the household in the case of social housing units. And we completed a questionnaire with the homeowner just to get some information about how the retrofit itself, the perceived impact on indoor air, and any other factors, I suppose, that could impact on indoor air quality and indoor environmental quality in general. We also asked and showed the homeowner or tenant to how to complete a diary. And this diary was really important because it was a diary indicating whether or not you know, certain activities were occurring over the monitoring period that could be perhaps related to the generation of indoor air pollutants, such as burning of fossil fuel, which was obviously happening pre-retrofit, or maybe candle burning or incense burning or smoking. So over the next few slides, I'm just going to talk to you today about the PM2.5 and the carbon dioxide measurement data. But before I do, I suppose I just wanted to mention that before or at pre-retrofit stage, it was quite evident to us, I mean, when we were in the homes, that occupant behaviours were going to have a significant impact on what we were measuring in terms of pollutant data. So at both pre and post retrofit stage, there was evidence of smoking and also vaping, even though the inclusion criteria was that we were looking for non-smoking homes. We did see evidence of smoking in some of the social housing units. And at post-retrofit stage, in the naturally ventilated homes, quite a number of tenants had blocked the wall vents. And then across all homes, but private and social housing units, that all of the homeowners or tenants had mentioned the handover, in particular that they felt the handover really wasn't adequate and that they were struggling, I suppose, with some of the new features of the retrofit, particularly the heat pump. So against that backdrop, I will just share the PM2.5 data. So what we have here is the the PM 2.5 data at pre-retrofit and post-retrofit stage. These are median concentrations in microgram per meters cubed. And I suppose how we interpret this is we are interpreting the data against the WHO, or World Health Organization, 24-hour recommended concentration limit of 15 microgram per meters cubed. So you can see that in the smoker homes at pre-retrofit stage, we're measuring quite high concentrations of PM. And at post-retrofit stage, these concentrations, sometimes they're increasing, but they're still quite high. They're well above 15 microgram per meters cubed. Whereas in comparison, the concentrations in the non-smoking homes are, in and around the 15, and there's no real significant difference at pre and post-retrofit. And just to look at this in a little bit more detail and considering the role of occupant behaviour, this is the top graph there is the pre-retrofit profile for one home, a social housing unit which had a smoker in the kitchen area during the monitoring period. And the orange line there is the kitchen profile for PM. It's the hourly concentration profile for PM 2.5, and the orange line is the kitchen profile, and then the blue line is the bedroom profile. So the tenant reported that they were smoking in the kitchen during the measurement period, and you can see that this behaviour. And I should also mention that the greyed out area is the nighttime period in the measurement data, and the area in between the two grey bars is the daytime period. And you can see that the behaviour of smoking significantly contributes to the PM concentration during the day period, particularly in the living area. And then if we move to post-retrofit stage, I've used a different axis now that the peak concentrations are much higher at post-retrofit stage. Here again, we have smoking in the kitchen, but the tenant had somebody staying with them, a family member staying with them, and they were vapor, and they spent most of the period of the measurement period in their bedroom, and they were vaping. So you can see the contribution of this occupant behaviour, vaping, to the PM concentration in the bedroom. So quite high concentrations during the day period at post-retrofit stage. And of course, this was one of the homes that had the blocked wall vents. So all of these factors, smoking, vaping, but also the blocked wall vents in combination with blocked wall vents, I guess, are, creating quite high concentrations of PM at post-retrofit stage. So moving on then to carbon dioxide concentration data. So I suppose here we're measuring concentrations of CO2 just to give us an indication of what ventilation was like in the rooms and how it changed from pre to post-retrofit. And particularly at post-retrofit stage, we did notice that a number of homes had blocked wall vents. And so we've separated out the concentration data into homes that have had unblocked vents, and then we have the blocked wall vents. And you can see this is the bedroom data in particularly, but we also have living room data there, and this is the median concentration at pre and post-retrofit stage. But you can see in the bedrooms in particularly what you'd expect, where we're spending most of our time, the concentrations are significantly higher when we have the blocked wall vents present in homes. So again, an occupant behaviour that's really impacting on the ventilation in those particular homes. And again, looking at this in a little bit more detail, here we have a stack plot showing the percentage of the concentration measurements that fall into the CO2 categories within EN 16798. And we present them per home. So Haven 1, 2 and 3 are the private mechanically ventilated homes, and Haven 21 and 22 are the social housing units that were mechanically ventilated. And then everything in between from Haven 5 to 19 are naturally ventilated. And we've marked with the red asterisks the homes that had blocked wall vents. And I suppose if you just really focus in on category 4 homes, so they're the purple colouring, because here we're looking at concentrations that are above about 1400 parts per million. And you can see that for some of them, for example, in Haven 7, almost all of the measurement data was above this value. And again, I suppose this shows that just very clearly that most of the purple areas are associated with homes that had blocked wall vents. We also have, I suppose, in Haven 19, a lot of higher concentrations of CO2. And in this house, they had a passive wall vent that was operated using CO2 concentrations. It didn't appear to be working, obviously, at the time. And we spoke to the local authority in question afterwards, and they had trialled this particular system in a number of homes, but was having problems in all of the homes with this particular system. Just to note as well that 5 of the homes, including the ones with the blocked wall vents and Haven 19, had mold issues, which was a new mold issue following the retrofit, which is what you'd expect when you've got under ventilation. And then just looking at the CO2 in a little bit, and this topic of ventilation and the role of occupant behaviour and handover in a little bit more detail. What we have here are 2 homes, Haven 13 and 14. These 2 homes were right in the same state. They were right next door to each other. They had pretty much the same retrofit measures, the identical retrofit measures completed on the homes, and they were monitored at the same time. There was 2 adults sleeping in the main bedroom in both homes. Now, Haven 13 really did not have a good experience with the retrofit. In fact, from the beginning, they weren't really in favour of the retrofit because they, I suppose, wanted to keep with the old system of heating their homes using solid fuel, fossil fuels. And even at the time of the surveys, showed us, their shed full of fossil fuel and so they felt that the retrofit was costing them money, and had all of their vents in the home blocked. And in particular, had great difficulty understanding the heat pump, and had told us that they turned the heat pump off on many occasions because they felt that it was costing them a lot of money to run. In comparison, their neighbour, Haven 14, overall, they had a very positive experience with retrofit, but initially did have some issues as well with regard to trying to understand the heat pump. However, they had a friend who was an engineer who they had told us had showed them a YouTube video on how to operate the heat pump, and as I said, overall had a more positive experience than Haven 13. So in Haven 13, we have blocked wall vents. Haven 14, at the time of the survey, the wall vents were unblocked, but they did say that occasionally they might partially block the vents because if to avoid, I suppose, smells from cigarette smoke that would be coming in from outdoors. But at the time of the surveys, they were unblocked. And if you look at the concentration profile for CO2 in the bedroom of Haven 13 over the monitoring period, and again, we've the grade portion of the graph is the nighttime, and you can see that the concentrations, particularly on night 2, are peaking at above 2,000 parts per million. And as I said, this is Haven 13, which had the pretty bad experience, I suppose, with retrofit and had the blocked wall vents. In comparison then to Haven 14, we can see that we've much lower concentrations of CO2 over the nighttime period in house 14. So occupant behaviour is clearly, very important to consider as part of retrofit. And we've analysed all of our post-retrofit data using mixed linear effects models. And we have looked at, I suppose, the role of different factors, such as occupant-related factors, such as smoking, blocking wall vents, window opening, frequency of window opening, and the retrofit itself. And if you look at, for example, the living room data here for PM 2.5, you can see that factors such as smoking, blocking wall vents, and blocking wall vents are significant contributors to the measured concentration. So they're significant factors that we need to consider. Even more important in terms of what we've measured than the actual retrofit itself. We've also looked at, the impact of ventilation type on concentrations of pollutants such as formaldehyde and radon. So, and the data seems to be suggesting that concentrations are lower in mechanically ventilated versus naturally ventilated homes. So just to conclude, I suppose our study, very much focuses on, is very much telling us that occupant behaviour is a significant factor, a significant predictor of indoor environmental pollutant concentrations, in particular where you have smoking, it very much will impact on the PM concentration. And then where you have activities such as blocking wall vents, that will impact on ventilation. So we have to, I suppose, consider this as part of retrofit. And it's not an easy thing to consider, but I think, or not an easy factor, or not an easy one to address. But it's quite clear that, I suppose, I think the general public have a more, seem to be closer to a closer and a more detailed understanding of the harmful effects of outdoor air pollution, but not as greater, don't have as great understanding or knowledge related to indoor air pollution. So this is something I think we need to work hard on, improving public awareness regarding indoor air quality, especially as we make our homes more airtight. And occupant behaviour in relation to smoking is really important in social housing, because we know that 34% of social housing tenants in Ireland report to smoke frequently indoors, compared to 14% of the national population. So this is a significant, this smoking in social housing, has a significant factor to play in terms of PM exposure. Also looking at handover, so that was a consistent theme, I suppose, across across the 3 years of the study. Homeowners were telling us that the handover was inadequate. They didn't understand how to use the heat pump in particularly. And I suppose if we don't get the and this isn't new to our study. I mean, this seems to be a persistent issue across the last number of years. It's been well documented in the literature. And if we don't get the handover right, this will encourage energy inefficient behaviours, which in the long term will have an impact on indoor environmental quality. So it's something we need to address. So just wanted to, for anyone who's looking for further details on any aspect of the study, we've just had the indoor air quality pre and post retrofit assessment aspect of Haven published in a journal called Indoor Environments, and this would be a good resource to anyone who's looking for further details on other aspects of the study. And just to finish, just to like to acknowledge all the homeowners who participated in the research, and also the Haven research team here at Galway, and also, of course, the SAI for funding the project. Thank you.
Brilliant. Thanks a million, Marie. So great insights there from the study of a number of homes, detailed monitoring going on. So without further ado, I'm going to pass over to our second speaker, which is who is Simon Jones from Air Quality Matters, and he's going to talk about the change in the framework, what good looks like through monitoring. So over to you, Simon.
So when I was trying to think about what to talk about today, I thought it might be interesting to set a kind of a global top-level down framing of where monitoring sits within our built environment. I'm very lucky in that I'm a generalist. I sit in this kind of middle ground between academia, industry, and policy, and it kind of gives me a unique perspective somewhat as to how these jigsaw pieces are fitting together. As such, I wear a number of hats beyond the Air Quality Matters consultancy and podcast. I sit on a number of organisations, including the AIVC and UK Centre for Moisture in Buildings and so on, and all of them are increasingly leaning on monitoring to give insight into the built environment. So I thought it was on that I set the theme of the talk. Even if we were just to take public buildings just as one subset of our built environment, in Ireland there's approximately 11,500 public buildings, give or take. This was established by consultants engaged by the OPW. And within that grouping, obviously, there's an enormous variety of even public buildings. So this is a graph from that OPW study. I don't know how well you can see that, but most of the tall bars on the left-hand side are taken up with education, primary, secondary, and tertiary education, the healthcare sector, and public sector offices and public spaces, and then a broad mix of everything else from fire stations to Garda stations and so on. So there's an enormous range of even those 11,500 public buildings. And even if we take just one subset of that, let's just take educational institutions. Within that, we've got primary and secondary schools, institutes of technologies, universities like Trinity College Dublin, all have enormous age profiles, enormous size profiles and use profiles. So the built environment is a really complex place. And within that frame, we have to try and establish what adequate and acceptable ventilation and air quality is. And we've typically done that through the intent of regulations and standards. And these tend to set a frame of the amount of fresh air that we need to provide to spaces to stop the buildup of pollutants over time, the removal of stale air to efficiently remove pollutants before they spread, control of humidity and temperature and indoor environmental conditions. And we do that generally through compliance with building regulations or adhering to environmental health and safety standards and so on. And as such, we have to create a language around our expectations, the intent of these standards. And that's where we see language like adequate and effective means of ventilating buildings shall be provided for the people within it. And the challenge there is that we start to say that we want good air quality outcomes. And how do we do that in the absence of monitoring spaces? Well, we do that by setting standards and regulations that talk about the performance of ventilation in order to achieve that general good outcomes. So in the commercial sector, we do that through the likes of CIBSE guidance, which I'm sure you're all well familiar with, like the likes of CIBSE Guide B and CIBSE Guide A. We start to supplement that with TM40 for health and well-being for building services, or even TM68 for monitoring indoor environmental quality. All of these standards and regulations and guidance documents set a theoretical frame of what we expect a good outcome to be. But just because we write a good document doesn't mean we get a good outcome. And the challenge here is ultimately the goal is to provide acceptable air quality for people, or adequate air quality for people. And this is where we tend to fall down. We don't have a lot of standards for what acceptable air quality is within the built environment. If I was to give you all a jar right now and ask you to close that lid on the jar and send it off to the lab, there wouldn't be anything that would come back that would tell you you were meeting certain standards. They could tell you what was in that jar and give you some guidance if it fell outside of, for example, occupational health and safety standards. But beyond that, there are very few regulatory thresholds for a lot of the things that we would consider pollutants within our indoor environment. And we're not given a choice often. When it comes to things like water and food, we can make a conscious choice to withhold consuming those for a period of time if we don't like the look of it or like the taste of it. We don't get that choice within our built environment. When you have a choice of 2 offices to walk into, there's very little way for you to tell the type of environment that you're walking into. And the same applies for homes, one home to another, same applies for classrooms and buildings and so on. And it's a real challenge. But nonetheless, over the last few years, what we've started to see is the development of standards around what we would call healthy buildings start to build up. And that's where we look at the likes of WELL and RESET and BREEAM and LEED and aerated, and the list goes on and on. Smart buildings, all of them have started to try and frame what good looks like. So within that, within the non-residential sector, we've had to start building up the business case for what good air quality is. And one of the things we do is we use the cost of business to build the business case of healthy buildings up. And one of the principal ways we do that is through the use of the 330 300 rule. And this goes back to an old real estate principle from the States that says, of a business, in this case, 90% of the costs of your business is going to be wrapped up within staff and salaries and benefits. About 9% of it within rental costs, and only 1% within energy of your total business costs. Yet we pour enormous amounts of money into making our buildings more sustainable and more energy efficient. And even if we're able to achieve 20 or 30% energy savings in real terms for the overall cost of business to the business, it represents quite a small fraction of a saving. Yet if we can start to demonstrate improvements in things like cognitive function and performance and reduced sick leave and absenteeism and the kind of things that affect staff costs and performance, the potential to have an impact on that business is absolutely enormous. So we've started to see this narrative being built up within the non-residential sector as an example, that healthy buildings have a practical business outcome. Behind that, we've started to see increasing standards and guidance coming in behind it that look to frame what good indoor air quality in the workplace might look like. And for example, the Health and Safety Authority of Ireland have a code of practice for indoor air quality. The challenge is in all environments, and we've talked about the differences in building types, even within a workplace, there can be many different zones and uses of spaces and breakout areas and open plan offices and individual meeting rooms and canteens, and the list goes on. Even within a building, it can be quite complex. Here's just one example of a project I was working on earlier this year, which was a nursing home. Within that nursing home, there are 24 different types of use spaces within that building, all segregated off, all with different approaches to ventilation, all with different sizes and occupancy spaces. Establishing what good looks like in that space or what adequate ventilation is can be quite hard. So under the code of practice, they say, well, you need to, for example, are there records of the ventilation commissioning and maintenance of performance of those spaces? And we know in the non-residential sector, we generally tend to run our buildings to failure, particularly from a ventilation performance perspective. So very rarely, in fact, never have I come across ongoing ventilation performance data for a building. So in the absence of that, the code of practice is looking for environmental performance, the measurement of things like CO2. So as a simple rule of thumb now from the code of practice, you basically got two choices. If you have mechanical ventilation and you can provide evidence that the system meets the required performance for each identified zone, then that might be all you need. But if you have mechanical ventilation only and you cannot provide that information, or you have naturally ventilated spaces, the reality is you're probably going to have to start monitoring those environments to demonstrate that they're performing. And this is where we're starting to now see an obligation for indoor air quality monitoring appearing within our buildings, not just to define business outcomes, but also to meet requirements for things like standards. The interesting thing about the monitoring landscape is that it's changed really dramatically, particularly over the last 10 years, not only at the high end for research level equipment where we can really get down to speciated levels of monitoring in live situations, but handheld devices at a practitioner level have improved significantly and come down in cost quite dramatically and can provide quite precise and calibrated measurements of indoor spaces. But most importantly, we've seen the proliferation and the reduction in cost of low-cost sensors. And that's really where I'm just going to finish off this presentation. The reality is now, most environments that we're going to occupy within the next 10 years will probably have some form of environmental monitoring happening. Marie was showing CO2 monitoring in many of the properties that she was looking at. Those CO2 monitors, this is an example of one here. This is a photoacoustic sensor, so it vibrates CO2 molecules and can measure the level of CO2 in the air. That little sensor is about the size of a skittle and now is costing under 12 euros to manufacture. So our ability to introduce CO2 monitoring into different devices and into more and more spaces has transformed. We start to see environmental monitors pop up everywhere. And the reason for this is that the power consumption of them is reducing dramatically, which means many of them can be battery powered and last for many years, even as much as 10 years on batteries. They have a range of connectivity options, which means we don't have to do data logging and go in and retrieve data. That data can be beamed live up onto the cloud and used in practical ways. And we have a whole wide range of ways of displaying that information, from traffic light systems to screens and tablets and dashboards, that enable practical use of that data in real terms. And it's not just CO2 monitors. We see things like temperature and relative humidity. This little sensor here in the top left-hand corner, that's that little dot on a circuit board there, just below my blue dot. That little sensor there, that whole board is the size of a postage stamp. So that little temperature and relative humidity sensor literally is appearing in mobile phones, whether it's being turned on and used or not at the moment. And we're increasingly seeing more and more sophisticated low-cost sensors that can measure particulate matter, formaldehyde, carbon monoxide, nitrogen dioxide, ozones, TVOCs, all appearing within one little white box and measuring our indoor environment. And this has real practical uses in our indoor spaces. To give just one final example before I finish off, we've seen an absolute proliferation of environmental sensors into the social housing sector. In the UK, I think it's going to be approaching somewhere around 1.5 to 2 million sensors by the end of this year will be in social housing. And the reason for that is we can demonstrate practical uses for that indoor environmental monitoring now. For example, with just the temperature and relative humidity sensors, we can spot fuel poverty. By the patterns that people heat and cool their homes, we can spot the early signs of people making choices that would indicate they're at risk of fuel poverty. We can see early signs of condensation, damp and mold. We can spot empty properties before they fall into disrepair. We can see the effectiveness of ventilation and the effectiveness of interventions like retrofit through this monitoring. And as such, it's built such a solid business case within that sector that they are paying for this data to go in to their properties. And increasingly, we're seeing a proliferation of consumer devices. Here's just a selection on the left-hand side, all of which are half the size of a mobile phone, cost less than 150 euros, and are putting data in the hands of the consumer. And there are many large housing providers in Ireland alone who have had fairly awkward WhatsApp groups set up complaining about the quality of new build homes because they might have felt drafty or the air quality might be poor. And it's a very different perspective arguing the case with argumentative WhatsApp groups when they've got data to hand. And this is what increasingly we're finding now, the narrative's changing at the consumer end of things. So I just wanted to finish up by saying, just imagine this world that within the next 10 years, whether we're in control of it or not, most of the spaces we occupy will be beaming out environmental data. And in that narrative, it doesn't matter whether your building was compliant when you handed it over. It doesn't matter how good your brand reputation was. You are going to live and die by the ongoing performance of the spaces that you design and manage and occupy. And that changes the framing of what good looks like. Thanks very much.
Brilliant, Simon. So very strong arguments for monitoring buildings, and also, I suppose, showing the scale of monitoring that is happening, in particular in social housing in the UK. So if anyone's any questions, join the post to Marie or Simon or Stephen next, then please put them in the Q&A function at the bottom of the screen there, and we will deal with them afterwards. So with that, I'm going to hand over to Stephen Carter from COADY Architects, who's going to talk about the RIAI Sustainability Challenge, and in particular, some of their experience around monitoring buildings to determine the actual performance. So over to you, Stephen.
Okay, firstly, thanks for inviting myself to present on behalf of COADY Architects. I suppose as a practice, we've been collaborating with the likes of yourselves, industry and academic institutions for a number of years, and contributing as well to research projects. Ultimately, they aim to understand how to better deliver more sustainable buildings, and across quite a number of typologies, because we work across a number of typologies, including education, commercial, health, housing. Today, we've kind of been invited to talk on our experience with post-occupancy evaluation. And obviously, I'll be focusing on our experience as designers. And we'll be looking at, I suppose, the importance for us as designers on the role that post-occupancy evaluation plays in understanding how our completed projects are performing and how they inform the ones in the future. And just say, rather than the technical aspects, which I think Marie has touched on quite well, really, in terms of monitoring devices and periods and stuff like that. I'd say our journey, if you like, began some years ago with a secondary school in Tullamore, Coláiste Colm. It was one of the first projects that we were actually invited in to look at evaluating the performance of energy saving strategies, as well as what were at the time emerging sustainable technologies. And that was, I suppose, a research project that was set up by the Department of Education. It was a 600 pupil new build secondary school, and we were installing and testing things like combined heat and power, biomass boilers, thermal solar panels, PVs, and it introduced us to a new world and new terms such as vampire loads, where we discovered the draw of power off the grid after hours that we hadn't necessarily seen before, unnecessary but hidden costs or draws on monitors and PCs and other equipment. This is one of the first schools as well that introduced CO2 monitors, or sensors rather, I should say, which were linked to dedicated opening vents to provide fresh air, while obviously attempting to control and manage heat loss. And as an evaluation project, it highlighted the gap between what we expected the performance to be and at design stage and what the actual performance was. And I suppose ever since then, it's established within our practice a role that post-occupancy, or POE, as I'll call it, plays, and to understand the performance gap, which is known as the energy performance gap, or EPG, and how to identify the culprits, as it were. And I think that's the essential importance of post-occupancy evaluations. And just before I go on to the next slide, I just note that obviously existing building stocks are coming under increasing focus for energy upgrades and decarbonization, as everyone is aware. And it's interesting that the RIAI Climate Challenge, which we're speaking on a little bit, advocates for post-occupancy evaluation to actually evaluate and to suggest future strategy for the fine-tuning of existing buildings. So it'll play quite an important part in that. Second slide here, I guess we've all seen images like this before, but it's a little reminder of where we are or where we're going. And at a time that the Intergovernmental Panel on Climate Change published not so far long ago its sixth report, which included projections of CO2 and greenhouse gases under various scenarios, and concluding that global warming, trying to limit it below the 2 degrees C this century, is unlikely under the current global government commitments, and to a point where we might see increases of 3 degrees C in the next 45 years in certain parts of the world. However, the good news is that the pace for change is being driven by legislation, certainly in the EU, in the form of the EPBD, and things, and incentivized as well through things like the EU taxonomy, which is giving markets a little bit more, I suppose, confidence in investing in sustainable assets. And so on to the RI 2030 Climate Challenge itself. We as a practice are signed up to that. It was published in 2021. It's a call for all design professionals to take a leadership role in addressing both the climate and the biodiversity crisis, and to provide, so protect assets for our clients going into the future. There are 10 indicators that are on screen, each with a definitive target. I won't read them out all, but the first 4 indicators, operational energy, embodied carbon, potable water, and biodiversity, have some of the biggest impacts. And in the case of the first 3 there, it's been the subject of post-occupancy evaluation at a recent project that we've carried this out in at Kilbride Court, which is actually a 40-unit housing scheme with a mix of 1, 2, and 3 bedroom social housing units designed to that standard. So up on screen now, we have some of the outcomes, I suppose, of the post-occupancy evaluation. COADY committed to carrying out this evaluation as part of achieving a gold standard under the HPI certification scheme. We carried it out over 12 of 40 units that were built. This is typically more than you would require as a minimum to get a gold, but we wanted to cast the net a bit wider. And this slide shows, I suppose, the results over a number of indicators. And it clearly identifies for ourselves as designers where the performance gaps are and where we need to focus our efforts. So once again, you can see on screen here some of the gap areas. Operational energy is there at the top. Embodied carbon and water conservation are ones that stand out. And just to understand this slide a little bit better, I just note that the RI 2030 targets are there in orange. The design targets are there in the middle, and then the actual performance on the outside column there. So as a practice, we're using this kind of information to identify a number of projects across all of the typologies that we work on and see how they might align to the RAI Climate Challenge and our own charter that we've recently sort of put together, and try and establish a baseline across our projects of where we actually are, and gain learnings from this. So looking at these figures here at Kilbride Court, operation energy in use, which was established from meter readings, it shows that we are below what we expected in design, from 87 to 109, or above as it is, and at quite a distance from the RI 2030 challenge. Embodied carbon was established through gathering of information through environmental product declarations, which I think people might be familiar with, and they were established from actual declarations provided by the contractor on site. And water conservation, again, is quite a bit below as well. In other words, that there's high water usage or higher water usage than we expected in design. We also looked at indoor air quality again, which I think Marie touched on a lot in her presentation, but it's something that I think as designers we have a certain degree of control of and able to provide positive impacts through good detailing and good ventilation and specification. Biodiversity wasn't measured here. It's not something that's required to be measured in the RAI challenge, but it is measurable, and it's interesting to note in the UK that they have legislated for projects over a certain size to be calculated and demonstrate a net gain of biodiversity. So having identified the performance gaps between design and reality, the next few slides that I just want to look at here just suggest ways that we might bridge those gaps. So the first one here is operational energy, and at Kilbride Court, the building regulations, as you can see, required us to achieve 109 kilowatt hours energy per meter square, typically. the RAI challenge is much lower than that at 35, less than a third. And on the right-hand side, you can kind of see a lot of the contributors to that, things like hot water, air tightness, U values. A lot of them are, I suppose, fabric-based, and therefore we take a kind of a fabric-first approach to designing our buildings for air tightness, for insulation, for window thermal performance, looking at thermal bridging factors and stuff to reduce heat loss through critical junctions. But other factors obviously do contribute, such as poor ventilation strategies and hot water. And therefore, on the left, you can see some simple measures that we can adopt that impact on the overall operational energy. And obviously, they not only save on kilowatt hours, but they save on the occupants' bills as well. So, you know, hot water, improving or reducing flow rates for hot water producing showers, for example, and likewise improving air tightness levels can have a significant contribution. When it comes to embodied carbon, as I said before, we rely on manufacturers' information, particularly as declared in their environmental product declarations. So the key here is to get EPDs from suppliers in the first instance at design stage, and then ultimately from contractors on site to assess how the actual products and materials used as built. And just to note that I suppose in Ireland now, there are many manufactured products, increasingly so, that provide EPDs, ranging from hollow core slabs, thermal blocks, concrete roof tiles, insulations. And over 60 materials were actually assessed in COADY with EPDs. And as I say, we try to use as much actual product information as possible. On the right-hand side, there's just, I suppose, an illustration of where COADY Court landed as through the POEs, which was carried out by Project Indicate. And as you can see, you know, it's at 718, and we're wanting to get down to 625. So we just use this as a I suppose, a platform to assess how that particular project might have achieved the 625. So we looked at things like introducing eco-cement or GGBS, as this is a largely concrete construction. It's you know, cavity block construction, and we got down to a figure there of 686. Obviously, not quite where we want to be, and this is all informing, as I say, our future designs. And then we looked at things like using, you know, less concrete in the substructure in the form of raft foundations, and also timber frame. And, you know, therefore we can assess how we could better improve on a similar type of project going into the future. As we've also seen, just in potable water, the gaps there were quite large in terms of what we expected from our designs. The current building regulations require us to achieve 125 litres per person per day, but the RAI target for 2030 is actually significantly lower than that, at 75. And I suppose on the face of it, that looks like quite a large gap, but in actuality, we can specify for low flow products, and where, you know, after the case, there's also, I suppose, retrofit options as well. And all these are relatively cheap. And we feel that that's one thing that we can actually achieve in terms of reducing litres per person per day down to the RAA targets. I also just mentioned there, it's in red there, rain harvesting, use of water butts is very important, very significant, and should really be introduced to all future projects. Just in terms of biodiversity, again, I say it wasn't measured here, but the climate challenge, the RAI climate challenge, does look for enhanced biodiversity. As I say, it's not currently measured, but it can be. And I think this slide is really intended just to just put out there a couple of sort of big hit items that you can actually implement quite readily, like to support biodiversity, like retention of existing native trees and hedgerows. That's I think we've experienced that as being a priority. Integrating developments into existing wildlife corridors, which you can get through development plans with the local authority. And obviously a big one nowadays, and it's very important as well, is to design nature-based solutions for rainwater and water runoff, rather than, say, underground attenuation tanks as a form of sustainable drainage systems. There's many other things that can be done there, but I'm kind of conscious of time. So in conclusion, I suppose we can't rely solely on modeling assessment, as it were, at design stage to ensure that performance targets are met. We kind of know that. What the gaps are is obviously established through post-occupancy evaluation. And through our own experience, we've been able to establish, I suppose, these 4 things on screen: operation, energy, and body corridor, water conservation, and biodiversity, as having some of the larger gaps that we can actually affect positively. And at the moment, we're using these findings to target the biggest impacting indicators across all of our projects, including some of the key actions that you see on the right-hand side that can be taken now. And so that drives our designs in the future forward. And this will not only result in reduced energy and CO2, but also improved health, well-being, and cheaper bills for occupants, which I think the other speakers have also touched on. And the last thing I'd like to just say is that post-occupancy evaluation and its implementation is a collective effort and requires shared learnings. And it's through these sorts of collaborations that we've established with the likes of yourselves and Construct Innovate and IGBC, et cetera, that this will happen. And hopefully that will provide us with more certainty in the future of our performance for all of our future projects. So thank you very much.
Brilliant, Stephen. Thank you very much. So that's great to kind of see a practical example of monitoring, but also lessons learned from that monitoring and how can achieve better performance of buildings afterwards.